Okay, so the input data vector is two-dimensional in this example. The input values are x1 of 0 and x2 of 0. They feed it into the two nodes. So there will be weights here. This one will be W1. The superscript denotes the index of the layer it is incident on. And then it's 0, comma 1. 0 is the index of the node that it comes from, and 1 is the index of the node it is incident on. This will be W1, comma 1 of 1, W2, comma 1 of 1. Similarly, you will have weights that go into the second layer. So this will be W0, comma 2 of 1, W1, comma 2 of 1, and W2, comma 2 of 1. So this is hidden layer. So the index for the input layer is 0. The index for the hidden layer is 1. And let's say we have one output layer. Okay, the output layer has one node. This is the output layer. Now in the output layer, you will take the outputs here. The output of the first hidden layer node, this one will be x1 of 1, and this will be x2 of 1. The subscript denotes the index of the node. The superscript denotes the index of the layer. Again, there will be weights here. In this case, W1, comma 1 of 2, W2, comma 1 of 2. Additionally, we will add a bias node. So there will be one more node here in the hidden layer which has no inputs but only produces a constant value. That will be x1 of 0. And it will have a weight here which is W01 of 2. And this way we will produce the output. This one will be x1 of 2. This is the value that comes out of the output layer. Okay. This is the notation we will be using throughout our discussion of neural networks. So it's important that you understand this notation. I went through it very carefully in the recorded lecture in the last week. It's also the same notation the text uses, and it is very important that you follow the notation in the right way because all our derivations will be making heavy use of this particular notation that we use. So you have little l will denote the layer index. This is l equals 0. This is l equals 1. In this case, the output layer will have an index of 2. More generally, capital L will denote the number of layers in the network. So the output layer will have an index of L equals capital L. The input layer will have an index of 0. And the intermediate layers will have index 1, 2 up to L minus 1. Now, the output values from each of the nodes will be denoted using the symbol X. So Xi of L will be the output of node I from layer L. The input will be denoted using the letter S. So this is S1 of 1, this is S2 of 1. Okay, this is S. The value that goes in will be denoted using the letter S. Similarly, the value that goes in here will be S1 of 2. And this theta is the activation function, like the tan H function that we discussed in the last lecture, that takes the input and applies the activation function and produces the output. So I hope everyone is familiar with this notation because it is very important in today's lecture.
I'm a bit confused. Why do we need the bias term in the second one?
We will always have a bias term. So here this is every input, every hidden layer as well as the input layer will have a bias term. The bias will have no input coming in. It always produces an output of 1.
But what's the, like, I understand why we have it on the first layer, but why do we have it on
It's always the same reason. It's the same reason. You don't want just a linear combination of the inputs. You want to add an offset. It's the same reason as why we have it for the input. Question?
Yeah, we know that it's talks about like the sentences. Layer number 1 about the data.
Here?
Yeah, what's that? It's x sub 1 layer 0.
Oh, did I? Yeah, sorry, it should be the other way around. I'm not using my notation correctly. Right? So 0 is the index of the node, 1 is the index of the layer. That was the question. Always the superscript will denote the layer index, the subscript will denote the node index.
Professor, during from the video, you also introduced hidden layer where sometimes use H.
That was in the very beginning for the two-layer example. But that was just to motivate it. From now on, every layer, the output will be denoted by X, the input will be denoted by S. So for node I, input into node I and layer L, the notation will be Si of L. Output from node I, layer L, you will have Xi of L. That will be the notation throughout. Now Si of L will be the weighted sum, will be the summation of say j going from 0 to d to the L minus 1 of xj of L minus 1 times wji of L, where d to the L is the number of nodes in layer L. So all this notation was introduced last lecture. Okay, what we are doing here is just taking a weighted sum. Every input here is just a weighted sum of the values incident on that node. So S11 will be X0 times W01, X1 of 0 times W11 plus X2 of 0 times W21. You just take a weighted sum like this, and that's how you get this value here. Right? That's what this expression is mathematically showing. So this is the forward pass in the neural network. Once you have an input data vector X, you have a certain set of weights, you can compute the output value by running this particular, by doing this computation over and over at each of the nodes. And Xi of L will be theta of Si of L. So what is happening here is you have an input data vector X. In this example, it's two-dimensional. You have the two values that go in here. This is just the bias term. You use this relationship to calculate the values that are outputted from the hidden layer. Then you use again this relationship to compute the value at the output layer in this two-layer network. Okay? So once you have the input and the weights, you can compute the output in this particular way. This is the forward computation that was discussed last week. Now, once you have this, you can compute the loss. So you have two things. You have model parameters. The model parameters are just a collection of weights, wi, j, superscript L, for all values of I, j, and L. This is what the model parameter is. You just take all weights in the network. This is the weights that you want to train. When you say you want to train the neural network, you want to compute all these weights. So there are 6 weights here, right? 2 on each of the from each of the nodes. 3 weights here. So you have a total of 9 weights in this neural network. That constitutes your model parameters, just the collection of all the weights. It's clear? This is what you want to learn from the training data when you train a neural network. Okay? Now, the other thing you need is to define a loss function, right? You want to optimize a loss function with respect to the model parameters. In any machine learning problem, that's how it is. You define a model, identify the model parameters, introduce a loss function, and optimize the loss function. So we have to define a loss function here. The good news is we can just use the same loss functions we used in linear models. So for example, if this model was used for regression, so if your training example was x comma y, you want to compute the loss on this particular example, what you would do basically is that you will take this x as an input into this particular network. You will compute the output value. You will compare it with y, and you will take the squared error. If this is a regression problem, you will take a squared error, and that will be your loss. Right? So this is the input example. You want to see how well this network performs on this example. How do you evaluate the performance? Well, you don't use y. Y is the ground truth. It is the label that you have. You take x, you feed it into this network, do the forward propagation, you compute the output value and see how close it is to y. And you compute the squared error if it's a regression. So E of omega will be the loss on this example, and in this case it will be x2 of 1 minus y squared. The same idea can be applied in other applications. If this is a classification problem, then your output will be a probability vector. You will be assigning a probability to each of the classes. Okay? And then your loss function will be the log loss function. So in that case, your output won't be a scalar. So in this particular example, your output was a scalar. Hope I got this wrong. This will be, the layer index is 2, the node index is 1. Right? So this is what the loss function will be for regression. Now if instead of this, imagine you had a classification problem. It was a binary classification problem. Then this would denote the probability that the label is 1. And then you would just use the log loss that we used in logistic regression. Right? So depending on the application, you can use a standard loss function. There is nothing different. There is no difference between linear models and neural networks when it comes to loss function. It's the same old definition. If this was a multi-class classification problem, you will not have a scalar here. You will have a vector here. The output will be a vector of probabilities. And then it will assign a probability to each of the classes. And then your output, basically, the loss will be the log of the probability you assign to the true label. And I discussed this in detail in the previous lecture, so I won't go over it again. I hope this is clear. The reason I'm going over this is because the notation is super important in today's lecture. So we will be used, if you get lost in the notation, that's too bad. So you should ask questions now. The good news, however, is that if you understand the notation, most of the remaining derivations is not too hard. It is just straightforward applications of chain rule in calculus and so on.
I have a question about the notation. So if you go to the next page where you have the loss, I don't understand the x sub 1.
This is the output. 2 is the output, is the layer, is the output layer. 1 is the one node we have in this layer.
Okay, so 1 is node number 1, right?
This is this one, yeah. 1 is the node index. 2 is the output, is the layer index.
Oh, okay.
So here, right here, output from node I, layer L is xi of L. Good?
So for exponents, there's no parentheses beside, right?
Yeah, parenthesis is, I should put the parenthesis for the layers and for nodes I don't, just to emphasize. But the main point is superscript is the layer, subscript is the node index. That is the important thing. For weights, wij of L will be the weight from node I in layer L minus 1 to node j in layer L. It will be the weight that sits on the edge connecting node I in the previous layer to node j in the current layer. And the superscript is the index of the layer you are incident on. Right? So you never will have W superscript 0 because there is nothing incident on the input layer. You will always have, the weights will have superscripts 1, 2 and so on up to the last layer. So I hope you will get used to it by the end of today's lecture. Okay, so let's say we want to train this algorithm, right? We have a training set. X1, Y1 up to xn yn. And then we want to select omega to minimize or at least approximately minimize this quantity. Right? This is the average error we get on the training set. If you apply the loss function to the first example, you will get E1 of omega. If you apply it to the second example, you get E2 of omega, and you want to minimize the average loss. This is always how we work in machine learning. Right? So now the problem is well defined. If this was the example we saw before, each En of omega is a squared error of this form. We'll put an example in, compute the output, compare it with the label, take the squared error, and do this for all the examples. Right? And then we select the weights that minimize. So in principle, this can be done, right? Because this is mathematically a well-defined problem now. Each omega gives you one value here, and select the omega that minimizes it. In the previous example, omega was those 9 weights. We had 9 weights here, so omega would basically involve finding these 9 weights on the 9 edges to minimize this quantity. For any neural network, it's the same thing. You just choose the weights and you minimize it, okay? So the standard way of doing this is to use stochastic gradient descent. In machine learning, when you introduce a model, introduce a loss function, you are in some sense done. Because the first thing to do is to use a standard, optimization framework, namely stochastic gradient descent, that can be used to optimize the loss function. So that's what we'll do as a first step. It may not always be the best thing to do. There might be cases where you can significantly improve the iterative optimization algorithm. But as a first step, it is the thing you would try. So we will minimize this using stochastic gradient descent. Okay. So what we do here is, in iteration k, say we are in iteration k, what we do is we select an example x and yn at random. So we have the training set with n examples, x1, y1, x2, y2 up to x and yn. In stochastic gradient descent, at each iteration, you select one example at random. Say we select x and yn. Then what we do is we compute the partial derivatives of the loss function with respect to the weights. So den of omega k by dwij of, so we are in iteration k. Let's say our model parameters are omega k. And what we do is we compute these partial derivatives for all values of I, j, and l. I haven't said how we will compute it, but let's say we compute it in this way. Then how will I do the update? Like what will come next? I'm at iteration k. Omega k is my current choice of model parameters, right? Now I'm going to pick one example at random. Say I pick x and yn. And then I do a forward pass. I compute the loss function, right, for that example. And let's say for now that I can compute these derivatives. For each weight, I can compute the partial derivatives. So in this example, I'm taking one input example. I'm getting the output value. I'm computing the loss. I'm computing the loss for this particular output. And then I'm taking the derivative of that with respect to the first weight here, the second weight here on this edge, the weight on this edge. For all the 9 weights, I'm computing this partial derivatives. I'm not going to tell you how to compute it as of yet. We'll see how to do it. But if I do this, then what is the next? What is the next thing to do in SGD? Why am I computing the derivatives? You update the weights, right? What you do next is you simply do weight updates. Let me write it on this page. You will take wij of L will be the previous estimate minus some epsilon times dEn of omega k by dWij of L. That's it. And then you continue until you converge, until some stopping condition is met. And we'll discuss what are the right ways of convergence later on. But this is the principle of stochastic gradient descent, right? Take the derivatives and with respect to the weights and do this update. So now the question is how to compute dEn of omega k by dWij of L. Any ideas how we could compute this? So the right answer is to use backpropagation algorithm, which is sort of the main topic we'll discuss now. But before that, if I did not know this sort of literature and I was just given a neural network and like the one we have here, let's say this is my neural network, I'm presented this particular graph and I'm asked to compute the derivative of the loss function. So I have to compute the output, then compute the squared error. So then I compute E of omega, which is x1 of 2 minus y square. I compute this from this output value. And then I'm asked to compute the derivative of this with respect to, say, the first weight here. How will I do that? Without knowing anything complicated, just based on this graph.
Expand your x1 expand your x1 because it's consistent with the sum of which. Just expand your x1.
You're saying x12 will have some dependence on this and try to, but that's too complicated. Let's say this graph is extremely complicated and if you try to do it, it's very difficult. Just numerically, how will you do it? Don't think of it algebraically now. I want to understand how this affects the output. Yeah?
Change x a little bit, see how.
Exactly. What you do is you try to wiggle this edge a little bit. So you will add some perturbation here, right? You will add a perturbation here. So say instead of this, you add some delta to this. Then you redo this calculation. You will get a slightly different output here, right? Because now this edge is, if there is no dependence, it will not change anything. But there is some dependence. So you'll get a slightly different value here. Now you'll get a different loss function because from that. And then you basically look at how big the difference is. Once you, so let's say you get some E prime. Once you perturb with this particular modification, so all the other weights are fixed, the same as before. You just add a slight change here. So we'll now get an E prime. So using E and E prime, how will you estimate the derivative? Yeah? Take the difference and divide by delta. That's the sort of the approximation you do, right? So that's basically the first idea. That this is known as a numerical approximation. This is a numerical approximation to the derivatives. It is used widely in the literature when your functions are not differentiable. So there is a whole body of work on gradient-free optimization methods. And what they do is things like this. They approximate the derivative in this particular fashion. So here you have to compute 9 partial derivatives, right? You will do this 9 separate times. At each time, you will change the weight a little bit, recompute the output by running the forward pass, take the difference in the errors, divide it by delta, and that will be the partial derivative estimate for that particular weight. You do it for the first weight, then you do it for the second weight, third weight, and so on. Each time just change that weight, keep everything else as it was before, estimate the difference. Questions?
Can you keep the delta the same? But not, right? You don't keep the delta.
Those are all second order questions. Should we keep delta? You could keep delta the same and fairly small, and that is the first thing you could do. If the magnitudes of the W's are different, it might make sense to change deltas accordingly. So there are ways of improving your accuracy, right? So the one question is about how good is this approximation, and is there a smart way of choosing deltas? Now the thing is, we will be happy with some small, reasonably small value that is constant across, right? So let's say that is fine because ultimately everything is approximation. SGD itself is an approximation to the true gradient. The learning rate itself is an approximation to a small quantity. So we are doing a lot of approximations here. This is also an approximation, and we are okay with that one. We are not too worried about it. What is a big issue with this? Why don't we want to do this in a real neural network? Like, what will be the bottleneck?
Time consuming.
Why will time consume? Why will it be an issue?
Because I think just for the imagine you have like multiple layers, right? And then for each activation function, you need to find that specific epsilon or like that small value bit.
Right. So what was suggested is you have to do this separately for each weight, and there will be in typical neural network there are millions of weights, right? If you look at one weight and see how much computation you do, you have to perturb this, keep everything else same, and then see what the output value is. That requires computation which is of the size of the neural network, which is the number of edges. So if you have million nodes, weights, then you will have to do million computations for computing each partial derivative. And you will have to do this million times. For each edge, you will have to do this forward pass, which will be million computations. So it will be million square, right? Total complexity for one SGD update, just to change like that epsilon d by dw, for one update in the SGD algorithm, you will need million square computations. Typically, neural networks wants 10 million or a billion parameters. This just becomes impossible. You're talking about, a day for one update. That doesn't work. Yeah?
Why we cannot just do an incremental update?
What do you mean?
So if I wiggle one path, one weight, then if I just follow through the trace, I could potentially.
You'll have to basically change all of them because if you change, because it basically changes all the weights here, right? Like if you change this, you add plus delta here, you have to go back and fix this. I mean, might be smarter ways, but this is the most basic implementation. In fact, what we will discuss next is the most efficient implementation that requires a complexity which is of the order of the number of edges, right? So there are ways to improve it, but this is the most basic implementation where we change one weight at a time, recompute the forward pass, estimate the derivative, move on to the next weight. You might be able to do something slightly smarter, but I don't see an obvious way because if you change this, all the computations will change. You go back and fix this and update this, then again other computations will change. So it might require some thinking, but what we will discuss is an algorithm known as the backpropagation algorithm. And this is a seminal result in the field, actually by a professor at U of T, Jeff Hinton. This is a reference. And this computes all the derivatives exactly, so no approximation. Complexity linear in the number of weights. So if you have like say a million weights in the neural network, you only need a million computations of the order of a million computations to compute all these partial derivatives simultaneously. You will need a million computations for the forward pass, as we saw in the previous lecture, because you are visiting each edge at least once. And so you will need the same number of computations, not only for the forward pass, but also to compute all the partial derivatives exactly. So this is the main idea of the backpropagation algorithm. It is one of the main building blocks in machine learning. And that is what made the training of neural networks so efficient. Now it's not a new result. It's still like 40 years old. No, 30 years old, not that old. Okay, so it's 30 years old, but so it was known a while back. But the problem was back then, despite the efficiency of backpropagation algorithm, the computational power was still not high enough to train very large neural networks with millions of nodes. Only when GPUs came in and clusters, people started using high performance computing clusters, it became possible to train such large networks using the backpropagation algorithm. So the impact of this algorithm was only realized maybe in the last 5 years when we had the computational power. And this is what created a lot of excitement in the field. But the theory has been around for a while. Any questions before we proceed? Okay, so let's understand the setting a little bit, and I will move on to the next page. So let's say that we are in one layer, we are in layer L of the neural network. This will have a whole bunch of nodes in layer L. There is the bias node where the output is always set to 1. And then there are other nodes. This is the first input node. So the input here is S1 of 1. This is S1 of L, S2 of L, up to the last one, which is SDL of L, right? Now, if you remember, what happens next is you compute the outputs by applying the activation functions. This will be X1 of L, X2 of L, up to XDL of L. Then this goes into layer L plus 1. Let's look at one node here as J of L. This is the input into node J with output Xj of L. All these are fed into a weight matrix W, superscript L plus 1, to get inputs into the next layer. We did this in the last lecture. This process continues until you go to the output layer, where we produce the output X of L, and then from this we compute En of omega, the loss function on the example of interest once we have the output. Okay? We will look at one particular weight that is incident on this node, Wij of L. So this is the weight coming from node I in the previous layer and incident onto node J in the current layer. There are of course other edges incident on it. So there is Wi minus 1 J of L, Wi plus 1 J of L, and so on. So there are many weights that are incident on this particular node is J of L. We are interested in this particular node, Wi comma J of L. And we want to compute the derivative of the loss E of omega with respect to Wij of L. That's what we want to compute. Okay? We want to compute dE of omega. Let's not worry about the subscript n. We'll just assume one generic example. We don't have to carry that by d Wij of L for all I, J, and L. But let's look at this specific weight. So intuitively, as we discussed before, we want to understand the sensitivity of this weight with respect to the loss function here, right? So to do that, let us look at how this weight propagates in the neural network. So if we were to change the weight here, it would change Sj of L, which would then affect the values in downstream. So everything from here will change if we change the weight Wij of L, right? But let's try to understand systematically how this change will happen. So if you look at the loss function, let's try to see how it is computed. The loss function can be computed once we have the output value XL, the weight from the output layer, and the label Y, right? That's how the loss is computed. It's only when we compute the loss, we do not look at any intermediate values. We just look at the output value and the label associated from the training set. So E of omega is just a function of X of L and Y. Now let me go back. Of course, X of L is computed by all the whole forward paths from the input all the way up to this layer. But let's say I make a cut in this network and I give you values here. I don't tell you anything in the past. I give you values S1 of L, S2 of L, all the way up to SDL of L. I tell you all the input values in layer L. Okay, this is something that is revealed to your algorithm. Can you still compute the value here? Can you still compute the loss? Can you compute XL and then the loss? How will you do that? You just run a forward pass from there. You don't need anything in the back, right? So if I were to write this formally, then I can write E of omega as being dependent on S1 of L, S2 of L, up to SDL of L. These are the input values into layer L, as well as all the downstream weights. I still need to know the weights going forward. So as well as WL plus 1, WL plus 2, up to W capital L. If I have this information, then I can go ahead and compute XL. I don't need the previous weights. I don't need WL, WL minus 1, and so on up to the input value, right? This is sufficient information. So remember, this is a weight matrix. It has a collection of all the weights in this layer. We used this notation last lecture as well. So once we have access to all these weight matrices in downstream, so WL plus 1, WL plus 2 up to W capital L, and the input values in layer L, I can compute the loss function. Is this clear? Okay. This will allow us to understand how Wij affects the loss function. So let's look at all these terms and see which of these terms are dependent on Wij of L. Is the first term dependent? Is the input into node 1 dependent on Wij of L? If I change it, does it change? It doesn't change. What about the second one? It doesn't change. The only one that changes is Sj of L. So there is one term here. We'll write Sj of L, which is dependent on Wij of L. What about these weights? What about WL plus 1? Are these weights dependent on Wij of L? No, there are some other parameters in the network, right? Your neural network has all these weights. So if you go back to this example, there were 9 weights in this neural network. If I change this, it's not going to change. It might change the values going down, but it's not going to change the weights. The weights don't change, right? These are just other parameters. We have to take partial derivatives with respect to all these weights. But when I had to compute the derivative with respect to these weights, I don't change these. These are all fixed weights here. So none of the downstream weights change. So none of these weights depend on Wij of L as well. So in this whole expression, there is only one term, Sj of L, that gets directly affected by Wij of L. So if I use the composition rule for computing derivatives, and if I want to compute dE of omega by dWij of L, then I look at how dE of omega is computed. It's computed as a function of these parameters. Only one of them is dependent on Wij of L. None of the others are. So how will I write the chain rule? Any suggestions? So if this is so, there is only one quantity here which depends on Wij of L. All the others are constant. So if I want to compute the derivative with respect to this node, this particular value, then I can compute the derivative with respect to Sj of L and the derivative of Sj of L with respect to Wij. And do that pass, right? Any questions about this? Everyone okay with this? Let me ask you a slightly different question now. What happens if Wij was not affecting just Sj of L? It was also somehow affecting S1 of L. Let's say you had a certain network where Wij, the same way it feeds into two nodes, not one node. It's not this network, it only affects Sj of L, but we have a different neural network where we force Wij to appear on two edges. So it affects node J and it also affects node 1. Will this chain rule still be valid? So now not only this node, but this node also affects is affected by a Wij of L. So you have two terms in this expansion that depend on Wij of L. What is the right chain rule to use? You have to add, that's exactly right. I mean, you will have to take the derivative with respect to Sj of L plus the partial derivative with respect to S1 of L and ds1 of L by dWij of L. In this case, it so happens that all the other derivatives are, the ds by dw terms are 0 because none of the other variables are dependent on Wij. But if you understand this, you can derive all backpropagation algorithms. This is the main idea behind it, computing partial derivatives in the right way.
You said that only Sj L term changes, right? But how about the terms on layer L1?
So the weights do not change.
The weights do not change, but Sj L plus 1 or like...
Those will change, but the way this parameterization is done is if you have all these variables, then you can compute the loss function. So the loss function is completely defined by all these variables.
Oh, I thought you can skip this. But
No, so S1, S2, so the input here and the subsequent weights are sufficient to compute the loss function. So you have to do the parameterization cleverly, right? But the way this parameterization is done, it is complete for computing the function E, and only one of the parameters depends on Wij of L. Of course, we are not saying that only this node changes and nothing else changes. If nothing else changed, E was independent of Wij. That doesn't happen, right? Is this clear? So this is a very important topic. If you go back and look at, we have posted previous exams on the course website. You should look at those exams. You get a lot of questions on backpropagation and deriving it. So look at last year's exam. This was taught as 521 last year. So look at the exams there. Look at some other, this course had several incarnations before. And so we have posted the right exams for you to look at. And do look at all the questions that were asked. Because many of them make sure you understand how this particular chain rule is applied and how the partial derivatives are correctly calculated. It's all about that. Any questions? Is everyone okay with this step? Okay, so question. Out of these two terms, which one is easy to calculate? Which one is very easy? Out of these two terms, one is immediate, the other is non-trivial. So which of these two terms is very easy to calculate? The second one. We'll see the second one is very easy. The first term is difficult, and we will develop a backpropagation algorithm that computes this. So if we want to compute dsj of L by dWij of L, then that is actually pretty easy. We just have to use the definition of Sj of L This is the summation of k going from 0 to the number of nodes in layer L minus 1. Right? Now what is this going to simplify? We can do a term by term derivative. What is this going to simplify?
Whatever the term multiplied by the W, just
Yes, so what happens is when k is not equal to I, the weights are different, the derivative will be 0, there's no dependence. When k equals I, well, the derivative with respect to the weight will be 1 and this will pop out, and this is just xi of L minus 1. So this quantity is straightforward, very easy. On the other hand, we'll let delta j be dsj of L by dwij of L. We'll define a new quantity delta j of L to, sorry about that, didn't write it properly, not this, the other term, will be d e of omega by dsj. This is the second term. This will be referred to as the backward message in the neural network. It will be the backward message at node J in layer L. This will have a significance because this will be computed recursively using the backpropagation algorithm in a backward way. So we'll start at the output layer and then make our way backwards to the input layer. And delta J of L will have a significance of being a backward message at this particular node. So the picture now we have is the following. We have two nodes. This is node I, layer L minus 1. This is node J, layer L. There is a weight here. The weight is Wij, comma L. You have Xi of L minus 1 coming out. The input here is Sj of L. Of course, there are other connections. There is theta here, the activation function, and that produces Xj of L. Now, what we are introduced, so this is the setup we have so far. This is all our notation, right? The output from node I in layer L minus 1, the input in node J in layer L, the weight between these two nodes, right? This is what we have. Now we have Xi is the message going forward on this edge. Delta J is the message going backward on this edge. So delta J is the message. So Xi is the message that goes out of node I. Delta J is the message that goes back in node J. Backwards. This is our interpretation of delta J. And the formula for the derivative, so dE of omega by dWij of L is simply Xi of L minus 1 times delta J of L. This is the formula we have. So to compute the derivative of the loss function with respect to the weight Wij of L, you multiply the forward message on this edge coming from node I in layer L minus 1 and this backward message that we just defined, delta J of L, which is going back from node J in layer L. It's just a product of those two. So at each edge in the network, we will have a forward message and a backward message. And to compute the derivative with respect to the weight, all you have to do is multiply those two messages. Is this interpretation clear? Any questions about this? good. I haven't told you how to compute this quantity, how to compute this at all. And this is where the backpropagation algorithm will be used. That will be used to compute delta JL in a sequential fashion. People still writing, or should I move on? Writing? Done? Okay. Anyone else writing? Okay, so this brings us to the backpropagation algorithm. So we'll start with a special case. We'll assume that we are in the regression setting with squared error. The rest of it, basically the same ideas will apply to any neural network with any loss function, but to keep things concrete and simple, we will start with this case. Also, we'll consider just the output layer now. We want to compute the output, the delta L at the output layer. So we want to compute dE omega by dSL at the output layer. That's our task right now. So the setting we have is, because this is a squared error, the dimension of the output layer will be 1. So we have a scalar coming in, goes through the activation, produce XL. Then this goes through the G function, which produces E of omega, which is G of XL and Y. In this case, it's XL minus Y square. This is how the loss is computed. You are at the output layer, you get the input into this last layer, which is the output. Apply the activation function, compute XL. Once you have XL, you just go ahead and compute the loss, the squared error, right? G is just denoting that, emphasizing the fact that the loss is computed with the output and the label coming from the data set. Okay, this is, and what we have to do is compute dE by dSL. Compute the derivative of this with respect to SL when E is evaluated in this fashion, XL minus Y square. Any ideas how you will do it?
You mentioned the weights don't depend. Like if you change, like if you start, it's just a chain of weight, which you kind of separate case by case. Like you start from the.
So I want to just compute this one value right now, dE by dSL. I'm not looking at previous values. We'll compute them after this. So all I'm doing now is I want to compute dE by ds. There is no weights here. SL is what comes into the output layer. I apply the activation function. I get XL. So in this pipeline, there are no weights needed at this stage. The weights will come in the previous step, right? On how SL is computed. So here SL is already generated, fed into the activation function. XL is produced. Once XL is produced, you just compute this quantity, and that is your loss. So I want to compute the derivative of this function with respect to SL. That's the definition of my backward message in the last layer.
And just open up your Excel.
Just to open up, so what will it be?
The activation function.
So basically, that's, as was noted, is pretty easy. This is straightforward calculus. So this will be dE. What I will do is I will first take the derivative with respect to XL and then take the derivative of XL with respect to SL, right? Because once I compute XL, then the output, the loss is directly a function of XL. It's right in here. Y is a constant. It comes from the data set, not from the neural network. So what is the first term? Well, it's just a derivative of this with respect to XL. Right? What's the second derivative? What's dXL by dSL? Well, it's just a derivative of the activation function. We'll just write it as theta prime of SL. So for example, for tan H functions, if theta of S is tan H, then theta prime of s is 1 minus theta square of s. Typically, the activation functions will be chosen so that all these derivatives are very nice. So tan h has a closed form activation, has a closed form derivative, which you can show is this. Sigmoid has a closed form derivative. They are all nice, differentiable, smooth functions. So computing these things is never a problem, right? It's under your control and you choose it to be a nice function. So the point is delta of L is trivial to compute at the output layer. So at the output layer, delta of L can be computed easily. And the reason is because the loss is directly a function of XL, right? It's directly a function of the output. And then SL to XL is just a direct relationship through the activation function. So this can be computed always in a very straightforward way. Now it was done in this example, but the same idea generalizes. Okay? So if this was, say, a log loss, then you had a vector output here, and you had g of xl and y to be minus log of the probability for that particular example, could still use the same idea. You could still compute the partial derivative with respect to xl, and then take the derivative of xl with respect to sl. So this is nothing specific to the squared error. Of course, this particular formula is for squared error, but the same concept applies to any loss function and any dimensional input and any dimensional Excel. Same thing will, and we'll see the generalization later on. Any questions? So we are good with delta capital L. Now the next thing is to compute delta at the previous layers in a recursive way. So we'll then go to layer L minus 1, L minus 2, all the way to the input layer and compute the backward messages recursively at each layer. That's the next step. Okay. So let's consider an intermediate node. So we want to compute delta I of L at an intermediate layer. So L is some value between 1 and capital L. So it's not the output layer, something before that. And I is the node that you're interested in. Okay? So let's look at this more closely. So let's say we have node I in layer L. And theta is the activation function. What comes in is Si of L. What goes out is Xi of L. We want to compute the derivative with respect to Si of L. We want to compute dE of omega by dSi of L. This is the quantity we are interested in. So we compute Xi of L. This feeds into layer L plus 1. So we'll have nodes here. The first one will be S1 of L plus 1, S2 of L plus 1, and so on. The last one will be SDL plus 1 of L plus 1. So we'll have a weight here, WI1 of L plus 1, WI2 of L plus 1, and this one here will be WI DL plus 1 of L plus 1. So you will have the input, Xi will be the output of node I in layer L. This will get multiplied by the downstream weights, and then that will be used to compute the inputs into subsequent layer L plus 1. So the first node 1 will have an input S1 of L plus 1, which will be this sum, plus of course other edges that are incident on it, and so on. This is the picture we have. Then this will propagate further all the way until the last layer where E of omega is calculated. Now what we will do is we will assume that we have access to the backward messages in layer L plus 1. So we'll assume that we have access to all the backward messages. Okay? And we will like to compute delta I of L in terms of the backward messages in the previous layer. Delta 1 of L plus 1, delta 2 of L plus 1, up to delta dl plus 1 of L plus 1. So what we will do is we have computed the backward messages at the last layer for capital L. Now what we will do is we will do a backward computation. So when computing the derivative with respect to Si of L, so when computing delta I of L, we will assume that by hypothesis, we have already computed delta 1 of L plus 1, delta 2 of L plus 1, and the last one, delta dl plus 1 of L plus 1. So we have the backward messages for all the nodes in layer L plus 1. And we want to see how to make use of these messages to compute the backward message here. And then if we can do this computation, we can just proceed and go back to the input layer. Okay, so it's 7:15 now. I guess everyone wants a break, or do people want to continue and finish this and then take a break? How many want a break now? Okay, let's take a break. Let's take a 10-minute break and then we'll continue.